For this last video on cubic surfaces, we want to look at the cubic surface itself and understand how does it actually look. And in this direction, we have already gained a little bit of experience, namely if inside P2, you look at the quadratic equation and you get actually a smooth quadric like this, then we have seen by projecting from a point on the quadric that it is actually isomorphic to P1. So in this case, I mean, we started with some equation inside P2, and then we could show the solution set is actually isomorphic to something simple, namely P1. The question is, does something similar work for a cubic equation inside P3? And our guess could be, like, what could be a simple identification of the smooth cubic? Well, we have something two-dimensional, so maybe X is just isomorphic to P2. Unfortunately, that's too easy. And we can actually show it cannot be isomorphic to P2 because, well, this X contains two disjoint lines. We have seen that not all of the, if you fix one line, then only 10 of the other lines on the cubic surface intersected. So there's 16 left which don't intersect it. So X contains two disjoint lines. But on the other hand, we have seen any two curves, any two one-dimensional closed subsets of P2 must meet. So this was actually general that somehow if in Pn you have two things whose dimension sums up to at least n, then they must meet. And so there cannot be such an isomorphism. Just not possible. So this is too simple, but it's almost true. So we don't get an isomorphism, but we get a birational map. So which ties us to one of the last chapters that we discussed. The proposition here is that any smooth cubic surface is birational to P2. And in fact, we write down, again, very similar to this projection from a point, we write down such a explicit birational map, or at least we describe it here. And the key to writing it down is to use one of these pairs of disjoint lines, L1 and L2. So somehow let's fix these for the rest of the proof. So L1 and L2 are disjoint. And then we give inverse rational maps from X to L1 cross L2 and from L1 cross L2 to X. And then, of course, we see, well, X is birational via this map to L1 cross L2. But I mean, these are just two lines. So these are both isomorphic to P1. So this is actually an isomorphism to P1 cross P1. And then, of course, P1 cross P1 is birational again to P2. And so if you compose all of these maps, then you get a birational map from X to P2. Then we're done. And so how does this work? How do we go from X to L1 cross L2? And the crucial idea was already treated in an exercise. Namely, this actually works in general if you have L1 and L2 inside P3 disjoint lines. So they just lie inside projected 3 space now. And A is a point in P3 which is not on one of the two lines. Then there exists a unique line, L, which goes through A and which meets L1 and L2. So this was an exercise, and essentially the exercise just boiled down to some linear algebra. And so given this point, we can find this line, and of course then the line intersects L1 in a point A1 and L2 in a point A2. And essentially the idea of the map from X to L1 cross L2 is you take A inside X minus these two lines. So now A is actually a point in the surface, but it's not on one of the lines. And you send it to this pair of intersection points, A1, A2, of these things. And so this is, by this exercise, this is a well-defined map of sets. And then you can check in coordinates, for example, that this is actually a morphism where it is defined. I mean, a priori, this is not clear. It's not obviously given by a polynomial, but if you write down coordinates everywhere, you can check that this map is indeed a polynomial. Okay. And so, or somehow a rational map, I guess. And so this is indeed a function like this. Okay, so this is one direction, and the other direction is of course must do the opposite. So somehow, when we have A1 and A2 given, so we have such a pair in L1 cross L2, then of course we can write down the line through them, and then this line, we expect it should intersect X in a third point, and we would like to send this here to the third intersection point of the line with X. So why, first of all, do we expect a third intersection point? This comes from the fact that X is defined by a cubic equation. And so somehow, if you restrict this cubic equation to this line, then you get a cubic equation on a P1. And we see, I mean, somehow the points A1 and A2, they, of course, I mean, they line on the lines, and the line sits inside the cubic surface. So they are solutions of this equation. And so in general, you would expect that the equation of degree 3 has one more solution, and this will be this A. And indeed, somehow you find this unique other solution, and this works unless you're a very unlucky situation that this line L through the points A1 and A2 actually lies completely on the surface X. This is the case when the equation restricted to the line is actually identically 0. And then you have infinitely many points, so to speak, and then it doesn't work. So somehow then the map would not be well defined. But certainly this doesn't happen very often. In fact, we're going to see in a second this happens exactly for 5 possible such pairs. And away from these 5 points, actually this map is well defined, and it's an inverse to F, also a morphism, and then you have these birational maps. So this explains how do you go from the cubic surface to this P1 cross P1, essentially. Okay, and so with this kind of sketch-off argument, we have already shown the cubic surface is birational to P2. But in fact, we can do even better, because we can show that the smooth cubic surface is actually isomorphic to P2 blown up at exactly 5 points. I mean, certainly if you blow up P2 at 5 points, you get something that's birational to P2. And then the proposition says this is exactly any smooth cubic surface can be obtained like this. So we have then essentially fully understood how the surface looks. And here, I just want to give a proof sketch. So somehow more details are given in Gottman's notes. So the first thing is, so we define these birational map. In fact, if we're a bit more careful, this F can be extended on all of X. So F extends to a morphism from X to P1 cross P1. And the basic idea is when A approaches, I mean, a priori, it's not well defined when A is in L1 union L2. And so when A approaches a point A1 in the line L1, then you can get the corresponding point A2 here by taking the tangent plane to the surface X at this point A equals A1, and then this tangent plane will intersect this line L2 in some other point, and you call that point A2. So essentially very similar to the case that we had here, we also saw that if we project from this quadric equation here, from a point on the quadric, then as we approach this point, what we actually must do is we take the tangent line to this quadric at the point, and then use this for our projection. And very similar here, we take the tangent plane to this, this point here and intersect to get our projection. So in fact, with a bit more care, this f extends to a morphism. So this cubic surface has a map to P1 cross P1. And what about the inverse map? Does this also extend? Well, it doesn't quite, because we see it had a problem being well defined exactly when this line L through A1 and A2 lies inside X. But we have seen this situation, you have two disjoint lines, then there's exactly 5 lines lying in X and meeting these two lines L1, L2. So there's exactly 5 points where this is not defined. So you have 5 points in P1 cross P1. And then again, it's another check that if you blow up these 5 points, then this resolves the indeterminacy of the map G. So we have seen this principle that if you have a rational map, sometimes which is not defined at a given point, when you blow up this point, sometimes it becomes well defined on the blow up. And this happens here. So if you blow up the 5 points, then you get an inverse map. This morphism here still works to the blow up, and then you get an isomorphism from X to this blow up of 5 points on P1 cross P1. Okay. So we would then have shown that X, the cubic surface, is the blow up of 5 points on P1 cross P1. And now the final ingredient is a lemma that we have shown, namely, this told us if you have P1 cross P1 and you blow up a single point, then this thing is isomorphic to the blow up of 2 points on P2. Okay, and so what we now do, instead of blowing up all the 5 points on P1 cross P1 at the same time, you blow up first 1 point and then another 4 points. And then this blow up of 1 point on P1 cross P1 is isomorphic to the blow up of 2 points on P2. And so this means you can equivalently start with P2, blow up first 2 points, and then another 4 points. 2 plus 4 is 6. So this blow up is isomorphic to a blow up of 6 points on P2. And I guess this here should be 6. Okay, and then it's right. So any smooth cubic surface is actually isomorphic to P2 blown up X, 6 points. That's important, not 5. Okay, and so so this finishes this proof sketch, and as I said, more details are given in Gutmann's notes. And so somehow, yeah, we can get any cubic surface X as this blow up of 6 points on P2. And then with this understanding, we can now finish this entire chapter, because once you know this, you can actually identify what are the 27 lines. Before they were a bit mysterious, but in fact, now we have that X is just isomorphic to P2 blown up at these 6 points. And now we can, well, P2 we understand very well. And so now we can understand what these 27 lines are. This is the last thing. So an interpretation of this. So let's say X is the blow up of points P1 up to P6 inside P2. So this is the cubic surface. And now what are the 27 lines lying in it? The claim is you get 6 lines just as the exceptional hypersurfaces. Because we have seen if you blow up P2 in a point, then it replaces this point by a P1. P1 is a line. And so you get 6 lines just from the 6 exceptional components of this blow up. Then, if you have a collection of 6 points in P2, then there's 6 choose 2 different lines through a pair of them, right? For any pair of points, you find a unique line, and these will in general also be different. So let's assume these 6 points are kind of in general position. Okay. And then a priori, these 6 choose 2, so this 15 lines would be inside P2, right? And now, if you go to the blow up, what you can always do is you can take the strict transform, which means a priori you remove these 2 points, and then this line is in the complement of the locus where you blow up, and then you take the closure again in the blow up. This was the strict transform operation. And so you get these 15 strict transforms, and they also are lines inside this X. And then finally, there was an exercise which showed that if you have 5 points on P2, which lie in general position, so no 3 lie on a line, then there is a unique conic. Sorry, this should be conic. We were talking about cubics too much. So somehow a conic, so a degree 2 equation through 5 points. There's a unique one. And so whenever out of these 6 points you choose 5, then you find first of all this conic, this unique conic inside P2. And then by taking the strict transform, you get this Qi lying inside X. And the claim is, and I mean, this is something that one has to, that one again has to check with these birational maps that we have seen. Even though it started as a conic, so a degree 2 equation, actually inside this X, the X is transported in some weird way into P3, lying there as a cubic surface. And then actually this strict transform of the conic becomes a straight line under this map inside P3. And so you also get lines like this. And now if we sum them up, we have 6 lines of the first type, 15 lines of the second type, and 6 of the last type. And then 6 plus 15 plus 6 is exactly 27. So we understand these are exactly the 27 lines that we were interested in. And then as a final kind of sanity check, we have seen this kind of pattern that, that every line in the cubic surface should meet exactly 10 other lines in the cubic surface. And in this interpretation, we can now see this. So for example, if you're one of the 6 first lines, so you're one of the exceptional components, then there's 5 lines like the green one here, which you meet, namely the 5 through the 1, 2, 3, 4, 5 remaining points like this. And of the blue ones, you also meet 5, namely for any of these 5 points, you can throw it away and then get this blue conic through them. And this conic also meets the red exceptional divisor EA at this point. And so you get 5 plus 5 equals 10 lines. Okay. Then one of the green lines, Lij, it meets 2 of the red lines, namely the exceptional hypersurfaces over the 2 points through which it would go. It meets 6 remaining lines, namely whenever you have under the, so there's 1, 2, 3, 4 points left. Whenever you take one of the lines through these 4 points, you meet. So for example, this line would meet the green line here. So there's 5 choose 2 equals 6 remaining lines which you meet. And then of the conics, you don't meet so many, but if you do meet the conic, well, if you have the unique conic going through these points, for example, it meets the green line here. And similarly, if you throw away the other point, then you also meet that conic. And so if you count, you have 2 plus 6 plus 2, which is also 10 lines. And then finally, if you are one of these blue conics, then what things do you meet? You meet the 5 red exceptional hypersurfaces through which you go. And then there's 5 more lines, LAB, which you meet, namely through this given point, which you don't go through. If you have one of the lines from this to one of the 5 other points, then it meets this blue thing in the second point. So for example, this here would meet in this point and so on. Okay, so I think this is the picture which you need to meditate over a bit to count this for yourself. But essentially the statement here is that from this picture here, you can now see what are the 10 lines meeting some other line. Then as an exercise, if you want, you can also see what are given 5 disjoint line, given 2 disjoint lines, what are the 5 other lines that meet them. Okay, so this was everything about the cubic surface, and we have seen in this chapter somehow everything came together to help us count these lines, and then also in the chapter about the blow-up, we have seen how can we interpret this cubic surface as a blow-up of T2 and 6 points. So this was somehow the culmination of this first part of the lecture. And now the next part will be defining this new theory of schemes and developing some of the modern language of algebraic geometry.